The first one here is actually a repeated problem from the last slide. We just saw it. I'll just re-put the answer here. Okay, next one, x squared minus 100 is x times x. Square root of 100 is 10, plus 10 minus 10. Next one, we have a common factor of 5. Take that out, it leaves x squared minus 16. X squared minus 16, x times x. Square root of 16 is 4, so plus 4 minus 4. And the last problem is unique and different than all the rest. There is a common factor, but it's a common factor of x. So we take an x out of everything. It takes 1 power off all the x terms. And now we continue factoring this. X squared is x times x. We want numbers that multiply to 10 and add to 7. So positive 5, positive 2. Now we're going to transition back to graphs of quadratic functions. Often when we're graphing functions, any functions, not just quadratics, we're interested in finding the zeros of a function. The zeros of a function are simply the x-intercepts of the function. Okay, so if I were to draw a parabola on this graph, then that's a 0, and that's a 0. Okay, so clearly we can find zeros from graphing a function. If I can graph the function, then I can visually look where it crosses, and those are my zeros. Okay, but we're going to provide you throughout the middle of this chapter with some other techniques to finding these zeros. And that's a large portion of this particular chapter. In this particular section, we're going to look at 2 techniques for finding zeros. One is simply going to be to graph it. Second is going to be what we spent all of our time on thus far. It's going to be factoring. So we're going to look at graphing first, as that's where we started the chapter with a couple lessons on graphing. And then we're going to start to transition into all these algebraic techniques. And for this particular section, we're just going to look at factoring. But there will be more as we go into this chapter. Alright, finding the zeros of a function graphically. Well, we have to know how to graph it. That was the idea behind sections 5.1 and 5.2, is that we learn how to graph these functions. So the vertex for this function is going to be at positive 3, negative 4. Right there. And then my squaring pattern is 1 squares to 1, 2 squares to 4. And that's actually good enough because we can see right where that landed on the x-axis. Okay, so our zeros are at x equals 1 and x equals 5. That's just right here and right there. Okay, that is a great technique, graphing is, if the graph crosses through the x-axis at a spot that's easy to read. Okay, it crosses through the x-axis at an integer value, say, and that's easy to do. If the graph had crossed the x-axis at some irrational number like 1.3246, you know, that would be an impossible technique. We wouldn't be able to do it. And it's why we're going to have algebraic techniques to find these zeros as well. But there are instances where graphing works rather well. Now let's leave graphing behind and let's go into factoring. Directions say we're asked to find the zeros of the function algebraically by factoring. To find the zeros of the function, we simply set the function equal to 0. We replace the f of x with 0. And now we're going to factor this as an equation to solve. We're solving this equation with a factoring technique. X times x makes x squared. We want numbers that multiply to that one and add to this one. So we're going to use -6 and +2. Now, if we have a product of two numbers and their answer is 0, then that means one of these two numbers must have been 0, because 0 times something is the only way to get 0. So what we do is we set this factor equal to 0, and we set this factor equal to 0. We add the 6 over, we get x equals 6. We subtract the 2 over here, we get x equals -2. There's our zeros. Well, we've also found, if we were to graph this function, okay, what we found is that this particular function is going to cross the x-axis at these two numbers. Okay, so there's kind of your graphical connection. These are the zeros. The solutions to this equation are the x-intercepts for this particular function. Okay, next one. I begin by setting the equation equal to 0. Okay, this one has two terms. There's common factors. What can we divide from each of these? We can divide a 3 and an x. So 3x squared divided by 3x leaves x. 18x divided by 3x leaves 6. Now we take each of these factors and set equal to 0. So here we just divide by 3, we get x equals 0. Here we add the 6, we get x equals 6. And that's done. Okay, next you see a couple of examples for you to try on your own. These are just like the two that we just did, just different numbers. Here I set equal to 0. I factor this. X is going to be -6, x plus 1. So we get x equals 6 and x equals -1. On the other one, set equal to 0. Take out a common factor of x. Set each of these factors equal to 0. X equals 0, that's solved for. This one, x minus 8 equals 0, becomes x equals 8. The last couple of example slides asks us if we can do essentially the same exercise that we just did, but in reverse. We want to see if we can write a quadratic function from its zeros. Okay, so I know that the graph of some quadratic function crosses the x-axis at 3 and -5. Can I write a quadratic function that has that property? Okay, so I begin by basically solving the problem in reverse. If I think that there were two factors and the factors gave solutions of 3 and -5, what would the factors have been? Well, to get a positive 3 answer, we would have had to have x minus 3. To get a -5, we would have had to have x plus 5. From here, we can FOIL multiply to get to our final answer. So x times x is x squared. X times 5 is 5x. -3 times x is -3x. -3 times 5 is -15. So we get x squared plus 2x minus 15. That's our quadratic function that has these zeros. One more example, same directions. Write a quadratic function with zeros +2 and -2. The +2 would be an x minus 2 factor. The negative 2 would be an x plus 2 factor. If I then FOIL these together, we get x squared plus 2x minus 2x minus 4. Our like terms in the middle here cancel out. So our function is x squared minus 4. And done.